This video provides an overview of all the research that we did at Telemic, now Wavecore, for the BLUESS project, with the aim of designing and prototyping an RF energy harvesting BLE device. It consists of 5 different elements. First, a microstrip antenna with 6 dBi of gain tuned to the frequency of Bluetooth, which is 2.4 GHz. Second, an RF rectifier, which is optimized to work with multitone and GFSK signals, the modulation used by Bluetooth. It operates in the frequency 2.426 GHz with a bandwidth of 2 MHz, which is one BLE channel. And its efficiency has been characterized and is between 10 and 60%. More on this later. The Custom Power Management Board, or PMU, is based on the BQ25504 chip, and it uses the MPPT algorithm to keep track of the input voltage with a value of 50% in this algorithm. The efficiency has been characterized to be at around 80%. The storage element considered for the project is an electrolytic capacitor, and we consider 2 different values, a small capacitor of 100 microfarads and a large capacitor of 470 microfarads. The BLE device that we use for the project is a good old nRF5240 dongle, and it can use both BLE and BLE mesh protocols. For this demo and for this project, we only consider the uplink case, in which we are transmitting packets into the mesh, and we can change the transmission power of the device, usually from -20 to 4 dBms. Those are the ranges that we operate with. Here you can see a bit more information about the antenna that we manufactured for the project. It has a 70 by 70 mm size, and as I said before, a 6 dBi gain, and you can check its S11 parameters that we characterized with the VNA. Moving on to the rectifier, which is one of the main contributions for the project. It consists of a matching network and a voltage doubler rectifier, where the lengths of the stubs and transmission line and the values of the capacitors have been optimized depending on the input signal and the central frequency. The input signal is GFSK, which is the modulation used by Bluetooth, with a bandwidth time product of 0.5. The central frequency is 2.426 GHz, which corresponds to channel 38. We purposely chose an advertising channel because the goal here is to use the rectifier for swept to be able to harvest directly from BLE signals. If we choose a different channel, the chances of having a Wi-Fi signal there increases, which in principle, it increases your chances of being able to harvest more power because there are more signals there, but in practice, your rectifier needs to be really tuned to the signal that you need to harvest, which is BLE and not a combination of BLE and Wi-Fi. On the left figure, you can see the measured efficiency of the rectifier for different input powers and different signals, 2, 4, and 5 multitone signals and GFSK, that's the BLE signal. And on the right side, you can see a schematic of the rectifier. The PMU is a custom board that is based on the BQ25504 chip, and it also has several resistors and several passive components to tweak the different voltage levels that it operates with. It uses the maximum power point tracking algorithm at a 50% value, which means that once every 16 seconds, it will collect a sample of the open circuit voltage. The minimum input voltage is 600 millivolts for it to start working, but once it's properly working, this can be reduced to 140 millivolts. In any case, what it does is just boost the input voltage from whatever value it is to 3.15 volts, and it is delivered to the storage element. We designed resistors around the chip to be able to control the different voltage levels that it works with, because it is able to disconnect the load, the BLE board, from the capacitor, the storage element, whenever the stored voltage is above or below a certain predetermined threshold, called the overvoltage and undervoltage thresholds, respectively. There is also a third pin, a battery OK pin, which is a logical pin that outputs high whenever the stored voltage is within a certain regular working level voltage, called the battery OK low to high or high to low pin, because it has some hysteresis. The different voltage levels can be seen here. Maybe the most important ones are the overvoltage, which is 3.15, meaning that the condenser will never reach more than 3.15 volts, and the OK values, which means that the OK pin will be high whenever the stored voltage lies within 2.85 and 3.05 volts. Finally, when the stored voltage is below 2.5 volts, the node will be simply disconnected from the capacitor. Finally, two different applications are developed for the node. The first one is a BLE advertising application which checks the battery OK pin. Whenever the battery OK pin turns high, it just advertises a regular BLE packet. The second application is thanks to a SHIS and it uses BLE mesh. It simply transmits a packet at a configurable period once the device is provisioned. Let's take a look at the demo. We have a signal generator which is generating random GFSK signals, so regular BLE signals with the same parameters following the standard, and a horn antenna with 8 dB of gain. The transmitter is set to have an EIRP of 20 dBms. Next, we have our prototype and we can change the distance between transmitter and receiver at intervals of 20 centimeters. Well, we actually can change at any interval, but there are marks every 20 centimeters. The transmitter is continuously transmitting at 1 megabit per second, and this is really key, as you will see now. Let's take a look at the link budget. We have our transmitter with the gain, we have our path loss, then we have the antenna gain, and then we have the efficiency of the rectifier, the efficiency of the PMU, and that's the actual power that is delivered to the BLE boards. You can see here the mathematical expression using free space path loss. The EIRP is 20 dBms. As I said, the efficiency of the PMU is 80%, and the efficiency of the rectifier has been characterized for different input powers, which means that our link budget, the power delivered to the BLE, is the one that we can see here on this table. So what happens when we use a regular BLE board as a transmitter to harvest from instead of this GFSK signal generator continuously transmitting BLE signals at 1 megabit per second? Well, we did these experiments and we had a node advertising every 10 seconds with a transmission power of 4 dBms. And what we saw is that the actual energy that you can get from each packet is super low, which means that because of the super low duty cycle of BLE, that's why it's low energy, by the way, it's not really possible to effectively harvest these signals because you're basically, for most of the time, just not be able to harvest anything. And that's why you really need to have a constant RF level to harvest from if you really want to charge your capacitor. And this is similar to what happens in solar, because in solar you are able to harvest much more because path loss is not that huge, and also because you have a constant level. Not at night, sure, but during the day you have a constant light level, which means that is why you can really harvest a lot. So we first measure what is the voltage at the output of the rectifier when the load is connected for different distances. And as you can see here, for low distances it's quite high, and for higher distances, of course, it decreases according to the path loss. When the voltage is lower than 140 millivolts, the PMU simply doesn't work. Then I connected the small capacitor of 100 microfarads and I measure what is the charging time from this capacitor from 0 to full for different distances. I connected one pin of the oscilloscope to the voltage value of the condenser, which is the upper line. The lower line is the pin OK voltage. So it will turn high whenever there is enough voltage stored at the capacitor. And there are always two different phases. First is the cold start phase, in which the condenser charges really slowly, and then the main boost phase, in which it charges much faster. The threshold for this is 1.5 volts stored at the capacitor. So as we can see, when we change to 470 microfarads capacitor, of course the charging time is much longer, and this is of course because, well, a larger capacitor can store more energy, but it charges much slower. So in this figure we can see what is the charging rates in millivolts per second for the cold start phase for different distances and for the two capacitors. One thing to note is that the small capacitor is not able to charge from distances of 1 meter and onwards. And this is because the capacitor is so small that it's not able to store any energy for the node to actually start doing anything. The charging rate for the main booster is also plotted in this figure, and you can see that because it's the main boosting, the charging rate is much higher. And finally, the full charging time from 0 to full capacitor for different distances and for the two capacitors is shown in this figure. And you can see that for the 470 microfarad capacitor, when we are at 1 meter and 40 centimeters, it can take up to 25 minutes to charge. The video is sped up, and of course I didn't show everything, but it took a while to do these measurements. For the second set of measurements, I start from a fully charged capacitor and I transmit a packet and I measure what is the delay from the capacitor to recharge again. And this effectively is my transmission rate, because the faster I can recover my fully charged capacitor, the faster I can transmit. As you can see, the voltage drop for the small capacitor is quite high, simply because it's not able to store that much energy. It is able to recharge quite fast, and you can see the peaks corresponding to the transmission in the first, second, and third advertising channel, spaced 1 second in between them. The first dip, however, corresponds to the node waking up, recovering its state, doing the pre-processing, waking up the radio, and so on, which is why that's great. We can check that the node is actually transmitting packets because, well, we see them in the stored voltage of the condenser, but we are also able to scan those packets. And as you can see, indeed, there's a packet transmitted every second on every advertising channel. Next, when we switch to the large capacitor, we see that the voltage drop is of course much lower. This is because compared to the full energy of the capacitor, the amount that it takes to transmit is much lower in comparison, and that's why the voltage drop is much lower. But on the other hand, it just takes much more time to recharge. Then, if we change the transmission power from -20 to 0 dBms, we can see that the drop in voltage is of course higher now because, well, of course, the energy that we consume in transmitting these packets now is much more than before. In any case, here I plot what is the effective recharge time after transmission, or effectively what is our transmission rate for different distances for the two capacitors. One thing to note is that after 80 centimeters, the small capacitor simply discharges after transmission, and this is because the voltage drop is so high that it reaches the under voltage threshold, and simply the PMU disconnects the node with the capacitor. For the large capacitor, it's able to continue working up to 120 centimeters, in which it reaches an equilibrium point, meaning that the energy that it stores is enough to just keep the node running. But after transmission, it simply does not recharge again. It just stays at a constant level, which means that eventually it will also discharge after a certain number of transmissions. Now we switch to the BLE mesh application and we provision the node. The node simply starts transmitting BLE mesh packets at a 10-second interval with a transmission power of -20 dBm after it's been provisioned. And this means that we now have a certain energy consumption rate on one hand, and on the other hand, we have a certain energy harvesting rate, which means that the balance of these two will dictate for how long we are able to transmit before we need to stop and recharge our capacitor. Of course, when the energy consumption rate is lower than the energy harvesting rate, this means that we are able to recharge our capacitor before the next transmission, and we can continuously be transmitting. And this happens from distances from 0 to 60 centimeters. Afterwards, given a certain number of transmissions, the energy stored in the capacitor will be so low that we need to charge again. And that means that in the time that we are recharging our capacitor, we will not be able to transmit packets. You can see here an elapsed time behavior of the node, in which for 120 seconds I plot if the node is transmitting or charging. And as you can see, when we increase the distance, the transmission time is much lower compared to the charging time. Even for 140, because we had the equilibrium from before, it is able to transmit until it just replenishes the capacitor, and then it's not able to recharge it. Which means that if we take an observation time of 1, 5, 10, and 15 minutes, and we are transmitting a packet every 10 seconds on paper, but effectively this depends on the balance of this consumption and harvesting rate, we can see how many packets are we able to transmit effectively. So as you can see here, of course, when we increase our observation window, we are able to transmit more packets, of course, but also we are able to transmit more packets than before because the charging time is fixed and it starts to be negligible when you have observation windows really high. In any case, the conclusions that we can obtain from this project is that, well, RF harvesting has a really big limiting factor, and this is actually two. One is the path loss, which is huge, take into account that for 1 meter is 40 dBs already of path loss. And second is the efficiency of the components. We are not able to have super efficient components simply because it's just a limitation of the electronics. When we have a 60%, 40 to 60% efficiency in our rectifier, this is great actually. This is good in the state of the art. And then chained to that is the efficiency of the PMU. So the chained efficiency of this is not going to give you a lot of power to harvested power. Second to that is also that the capacitor that we choose, of course, there's a trade-off in there. Large capacitors are preferred because even though it takes more time for them to charge, once they are charged, they can store much more energy. And that means that if your energy harvesting is interrupted with the amount of energy that it has stored, it will be able to continue transmitting for a certain period of time. In any case, the harvesting versus consumption rate needs to be evaluated for every application in order to be able to choose the right capacitor to use. And then finally, the last conclusion is that you really need to have a continuous friend node transmitting a constant level to harvest from to be able to do anything, because otherwise, if you rely on sporadic low duty cycle transmissions, you will not be able to charge your capacitor. This concludes the BLUESS project. Thank you very much.